experience using semantic patches for Java program transformation. So firstly, I'll describe what a semantic patch is. Semantic patches were introduced along with the tool Coccinelle over 10 years ago for the purpose of automating widespread changes in C software, specifically the Linux kernel. So Coccinelle is a program transformation tool, and the idea of a semantic patch is to abstract away details and variations at each transformation site. So these are things like irrelevant details such as variable names that would differ between different transformation sites. Because of the user-friendly design of Coccinelle, it has received wide adoption, and there are over 6,000 commits in the Linux kernel that has mentioned the use of Coccinelle. Semantic patches are specified in the Semantic Patch Language, or SmPL for short. This is a DSL for program matching and transformation. It is designed to look very similar to patches produced by the Div software, and as such, it should be very familiar to developers who use revision control software. And here we have an example of a semantic patch. The intent of this semantic patch is to match and remove local variables that exist to just return a constant. On the left side of the slides, we have the semantic patch specified in SmPL. It looks very similar to how a patch will look like when you produce it with Div, or like when you look at Git Div. So a semantic patch consists of two parts. In the first part of the semantic patch, we describe meta variables. Here we declare three meta variables, a type T, a constant C, and an identifier red. In the second part of the semantic patch, we describe the changes you want to make in terms of pluses and minuses. On the first minus, we remove a declaration of a local variable that's assigned to a constant, and then in the last line, we modify the return statement such that it returns the constant directly instead of the local variable. Key to this semantic patch is the use of the ... operator in between these two statements. This abstracts away an arbitrary sequence of statements, and we add a constraint on this sequence such that it does not use or modify the local variable red, and therefore making this transformation safe. So Coccinelle will take this semantic patch as input as well as the entire project, and then it will locate cases where this semantic patch would match the code, such as the code or that I labeled with original code, and then it will produce a patch that will give us the modified code in which the local variable is removed. So the goal of our research is to explore what can be done for Java programs with the Coccinelle approach, and hopefully we could have some significant practical impact, much like how Coccinelle was useful for Linux kernel developers. We inherit several design goals of Coccinelle. For example, Coccinelle 4J should fit with the habits of existing developers, and it should be usable on a typical developer laptop. Also, Coccinelle is designed to be used in an iterative manner. As such, you would refine your patch based after inspecting what Coccinelle outputs. As such, there should be a short feedback loop, and Coccinelle 4J needs to be kept fast. And of course, the key feature of Coccinelle and Coccinelle 4J is that it allows constraints and matching on control flow paths. So in the first phase of our development, we target middleweight Java, which is a formal model of Java that is both minimal and valid, and therefore it represents a very useful first step for us. One observation we made is that much of Java's syntax is already found in C, so actually without any changes, Coccinelle can already pass a very small subset of Java programs. Furthermore, Coccinelle ignores code that it cannot pass, and it recovers from past errors, and it skips code that it cannot transform, moving on to code that it can handle. And this allows us to implement our features on top of Coccinelle in an incremental manner, as we could just simply ignore the parts that it still didn't work on yet. In the second phase of development, we wish to allow Coccinelle 4J to pass and process a wider range of Java programs. And as such, we target exceptions, which are used heavily in the real world. So we added some rudimentary support for control flow with exceptions. And here we have some basic example of what that looks like, in which we handle try, catch, and finally. An important feature of Coccinelle is the feature of isomorphisms, which in Coccinelle allows the matching of semantically equivalent code that are expressed syntactically differently. So this would be things like I++. You would probably want that to match against an expression that said I plus equals to 1 instead. Although they are different, but they probably represent the same intent for the developers. So for Java, we added things like A dot equals to B should match against B dot equals to A, although they are not exactly the same things. Another concern we tried to use isomorphisms to solve are that names can be qualified differently in different projects. For example, the square root function could be qualified in multiple ways, including a fully qualified way such as java.lang.math.square root, or with the class name math.square root, or just square root. As such, if we want to match against all the cases that they can be qualified, the semantic patch will be very verbose, as you have to write all the cases that we want to match. As such, we use isomorphisms to deal with this. We provide a script to generate isomorphisms based on how names are qualified within a project. And then one thing to note is that isomorphisms can all be disabled on an individual basis. So if it results in matches that you didn't expect, you could just turn off the isomorphism. We added some limited support for subtyping in the third phase of development. This is built on top of Coccinelle's handling of type defs, which in C allows developers to introduce synonyms for types. As Coccinelle works by passing files one at a time, we only use information within the same file, and therefore we only know that the type that the variable is declared with, and we ignore the inheritance path of our identifier's class. Doing so allows us to not incur the cost of type resolution, which may be expensive, especially if classes from third-party dependencies may be referenced. In practice, this is not a problem, as Java developers often refer to variables by their interfaces. So this is an example of what I mean. So this is some typical Android code, and then you initialize a new linked list, but then you declare it with the list type, which is the interface of linked list. So Coccinelle is aware of both these types, that this result variable is both a list and a linked list. Now that Coccinelle can work on a pretty large amount of source files, we wish to investigate two research questions. Firstly, is SmPL expressive enough to perform widespread changes in Java projects? And secondly, how much development effort can a developer potentially save by the use of semantic patches? To answer these questions, we target transformations made for migration of deprecated Android API methods. As Android is very mature by now and it evolves very quickly, there's been many APIs that have been deprecated. And we also know that there are a large amount of open source Android apps. So it's a very useful study for us. In the first case we look at a deprecation of on-console message in WebChromeClient. On-console message is executed by the Android framework as a callback, and typically it is only overwritten by developers for custom processing of log messages. In this deprecation, it is replaced by a method with the same name but with a different set of parameters. And here is some example usage. So in this case, the developer has declared a new anonymous class and has overwritten on-console message. So to correctly transform this case, we will need to change the parameters of on-console message as well as update the users of these parameters within the method body. And this is what the semantic patch to do that will look like. In the first part of the semantic patch, we introduce 3 meta variables, each one for one parameter of the deprecated method. And then in the second part of the patch, we describe the changes we wish to make using pluses and minuses. Basically, we replace the parameters with a new parameter, and then we use a variant of the ... operator, which I described earlier. In this case, we use this to indicate that all matches should be replaced. And for the replacements, we describe it using a disjunction, where each case of the disjunction represents one mapping that we would like to make. So the first parameter is replaced with an invocation of the method message on the new parameter, and the second parameter is replaced with an invocation of the method line number on the new parameter. And this is all very declarative, so this does exactly what this is. So this is the output produced by Coccinelle 4J. So as described in the semantic patch before, the parameters are transformed, and the users of the original parameters are replaced in the method body. In the second case we look at the deprecation of setTextSize, which is replaced by setTextZoom. So in this case, the method name has changed, but more importantly, the method parameter has changed as well. So what was used originally was an enumeration, is now an integer. And the mappings of the enumeration values to the new integer values are actually given in the Android API documentation. However, some difficulty here is that setTextSize may be invoked as part of a chain of method invocations. For example, setTextSize here is invoked on the return value of this.getSettings, and therefore we have to deal with this in a special way in Coccinelle. So here's what the semantic patch will look like in a modified code. So the key idea here is that we use a meta variable of the expression type instead of using the identifier type. So here, the expression E would bind to the invocation of this.get settings. And as E is present in both the addition and deletion code, it is not transformed. The semantic patch looks almost similar to the previous case, in which we describe each case to transform in terms of a disjunction. But here we see the need for isomorphisms due to a variation in how largest is qualified. The following 3 lines are semantically equivalent code, which only differ in how largest is qualified. So without the use of isomorphisms, the semantic patch I described earlier, which is on the right of these slides, would only match the third statement, where largest is not qualified at all. If we wish to match against all 3 cases, we would actually have to specify a disjunct for each case for how the names can be qualified. So for ease of expression, such that we don't have to express all the different ways a name can be qualified in the semantic patch, we generate the following isomorphisms. So what will happen here is that Coccinelle would take the isomorphism in the semantic patch, and the term largest will be expanded to textsize.largest as well as websettings.textsize.largest. And therefore, this makes it possible to match against all 3 cases with this semantic patch. So in total, I've only talked about 2 cases, but in the paper, we looked at a total of 6 cases. And then we evaluated them in terms of the development effort saved, the performance of our tool, as well as the ease of expressing SmPL. In terms of development effort saved, it increases in proportion with the number of replacement sites. So we look at the ratio of the lines generated to the semantic patch size. And for some of them, this ratio is quite small because each project only had a few invocations of the deprecated method. However, if we consider the set of all Android repositories, then each match would have numerous matches and transformation sites. And furthermore, the amount of code change is an incomplete measure of the amount of development effort saved, as Coccinelle also helps to locate the files that requires changing, as well as the correct locations in these files to change. In terms of performance, Coccinelle 4J performs quickly. These 6 projects represent over 300,000 lines of code and 2,000 source files. And the time to apply a semantic patch in each case is negligible, even in the cases where we have to modify multiple transformation sites. In terms of the ease of expressing SmPL, we compared our tool and SmPL against 2 existing tools, Spoon and Refaster. Spoon is a program transformation tool, and Refaster is a refactoring tool introduced by Google. Compared to these tools, against Spoon, transformations in Spoon have to be described imperatively, whereas Coccinelle takes a more declarative approach. And this makes it easy to represent a change. Compared to Refaster, SmPL allows the interleaving of addition and removal of code in the same rule, and it makes it easy to position code changes in a long series of code elements. And fundamentally, Coccinelle 4J differs from these tools in that it allows reasoning and abstraction over control flow. However, we also observe several limitations with Coccinelle. Because right now there's only limited support for reasoning about types, this leads to some unintuitive results sometimes. For example, if you try to match a collection, if you specify a collection in your semantic patch, it will not match against use of array list, because when Coccinelle 4J is trying to apply the transformation, it is not aware that an array list is a collection. However, this is usually not a problem for us because, as described earlier, usually array lists are declared with list. So if you change a semantic patch to use list instead, then it would match. Furthermore, Coccinelle 4J is provided on a best effort basis, so there's no proof of correctness. However, we think that this is mitigated by a fast iterative development process. Earlier, we see that Coccinelle 4J performs quickly, and this quick process encourages exploratory programming, much like using a wrapper. And in large projects where Coccinelle 4J will be most relevant in, there's likely to be a strict testing and code review process where breakage can be detected. But ultimately, Coccinelle 4J leaves it up to the developers and the compiler to detect breakage. To conclude, I talked about our experience with semantic patches for Java program transformation. We prototyped Coccinelle 4J, and the goal of our work is to explore the Coccinelle approach for Java. It's undergone 3 phases of development so far, and we have evaluated it using a case study of migrating deprecated Android API methods. To find out more about SmPL and Coccinelle, you can refer to the first URL. And currently, the development of Coccinelle 4J takes place on a second URL, on a fork of the original Coccinelle. Thank you for your time.
Do we have questions?
So in one of your examples earlier, you introduced a new identifier to in the parameters list to capture the new console message class that was needed. I was just wondering if you have, or if Coccinelle or Coccinelle4J has any support for freshening of identifiers that you're generating, because I can imagine you could be applying this to, say, a method called onConsole message that also introduces a variable called CM further down in the program, and that could lead to rather subtle failures in the new code.
Yeah, so actually Coccinelle has a feature to support this. If instead of specifying identifier, I said fresh identifier, then Coccinelle will actually introduce this with a different name such that there's no conflict. But in this case, it's just for simplicity and for ease of illustration.
Thanks for the interesting experience report. I know the original Coccinelle tool has an interesting front end because it wants to work on C code before pre-processing. Right. It's very important to be able to handle things before you've eliminated hash defines, etc. But in Java, because in a way Java is a cleaner language, you don't have that problem. Java code doesn't have a notion of being pre-processed. So I wondered whether you could have benefited from using an existing mature Java analysis framework to implement this, and whether you essentially wanted to extend the existing tool, or whether there are other reasons why you extended the existing tool rather than building something on a, say, more mature framework that would allow you to know more about the program you were transforming.
We wanted to let Coccinelle do the heavy lifting of matching the CTL and the control flow graph, but it's certainly possible to actually integrate it with other tools, I guess. So that's a natural next step for this work. But right now, the idea is to fill a space in the Java ecosystem in which the existing tools don't let you reason about control flow very easily, and Coccinelle lets you reason about that very easily. So we just did a logical thing and just build this on top of Coccinelle.
Cool.
Okay, so let's thank the speaker again.